So, how exciting. Okay. I want to go to the notes from last time. Are these the notes from last time? Yes, they are. All right. Is it time? It is time. 10:01. So, welcome back to the course, everybody. Oh yeah, today I announced on the website we have the Blitz presentation. So is there anybody online who wants to do a Blitz presentation? Rashana, you're unmuting? No, you're muting again. Okay, anybody? No?
I was just starting, so it was already unmuted. Sorry.
Yeah, I see. Okay. And you talk to me, Catherine, you do it later, right? So then, yeah, so that's fine. Good. So then last lecture, we had this wonderful presentation from Natalia Komarova. She's an absolutely amazing researcher, but also, and I notice she thinks differently than I do. So Natalia really thinks in these arrow diagrams, right? In the structure, which inhibits what and which supports what and how. So she thinks in these graphs. And then the mathematics, which is underlying, is just a tool for her. But she uses the models to better understand these graphs. So I found this very inspiring. I'm different a little bit, so I like to I like to understand things using differential equations, and it's more comfortable for me to do math this way. So, anyways, let me just close the door here because there's a conference, and if they get into a coffee break, then this will explode with noise. Oh yeah, and then I change the orientation on my tablet and everything is bigger. Nice. Okay, so we were in the middle of the Michaelis-Menten enzyme kinetics picture. And this is essentially what Natalia would love to do as well, right? We have an arrow diagram, we have a substrate and an enzyme, and they react to a complex C, and then the complex kind of degrades into a product, and we get the enzyme back. And that's the idea of an enzyme, right? It is a catalyzer, and you get it back after the reaction. And the goal is to transform the substrate S into the product P, because a product is useful for whatever. So it could be ATP, an energy molecule for the cells, etc. So this is a very important biochemical reaction and also a very typical biochemical reaction. And so last time I did some modeling, so we wrote down the differential equations for this. Yeah, let me recall this here. I called this. So Michaelis-Menten model, and these were 4 equations for the 4 ingredients which we have, S, E, C, and P. And you get these equations just by balancing all the transition terms, etc. And then we found we have a conserved quantity, which is E0, which is the total enzyme number or the total enzyme concentration in the system, which is an important number. We had another conserved quantity, which was S plus C plus P, which is not an important number, but it is still conserved. So there we go. And so using this constant E0 and the fact that the P equation decouples, we could then reduce the entire thing to 2 equations. And so this is all from last lecture. And this is system number 1 right here. And this is where I like to start. So I like to start to apply system 1. And also to introduce a method of singular perturbation theory using outer solutions and inner solutions and slow manifolds and all that thing. So it's a certain technique which I take the opportunity to introduce here. So some of you have seen this in other classes for sure, but maybe not all of you. And it's an important method. It's used all the time. We have system number 1. But I start a new file. Just uploaded again. I hope the others are uploaded too. Need to check. Are they? Thank you. Okay. Yesterday they came. Yeah.
Let me write down this model again. Yeah, and instead of t, I called it tau because we did a non-dimensionalization.
Transform the time.
And I just write down the same system.
Now this is a 2x2 ODE. So, I mean, what could be simpler, right? It is not entirely linear. We have nonlinear terms, y times x in both equations, but still. So you could do the standard thing which we did earlier, look for steady states, look for their stability, draw a phase portrait, and all this is possible. But all this is boring because we did this already. And I want to show you a new method. So show you a new method. And we use initial conditions of x at time 0 is like, call this x bar, and y at time 0 is y bar. Okay. So the idea of singular perturbation is as follows. Oh, and I forgot an important thing here. I forgot the epsilon. If you go back to the other page, we had an epsilon right here, and this will turn out to be important. So I put it in red. Singular perturbation. The idea is to identify different time scales. A fast time scale and a slow time. Fast means this is something which happens initially, if this is time, and this is x and y. And the slow time scale or the long time scale would be for long time, fast and slow. Or they're also called, depending which kind of. And I will show you methods how to compute them in just moments. This. Okay, so one of the curves is x, one is y. Not specifying which is which. But then, of course, the question arises, actually, what happens in the middle? Okay, so we get something for short times, we get something for large times, but what about intermediate times? And this intermediate times needs to be chosen in a way so that they fit together, right? And this fitting together is called matching. So we have to do three things. We have to do a fast solution, a slow solution, and a matching. And I do this in this order. I think I start with the outer problem number 1, then I do the inner problem number 2, and then I see if I did everything right and this matches. And this is how life works. So if you are ever in a situation where you try this, you do the slow, the fast, and then you see if it matches. And it is entirely possible that it doesn't. I had a student last year over the summer, actually Alexandra, you know her, you met her a few weeks ago. So she did such a problem and it did not match. And then, oh God, what do we do? So we had to find other methods to tackle this. See if.
Okay, so what does this mean? We assume that epsilon is small, so that the initial substrate concentration is large, the initial enzyme is small.
That's the very point of an enzymatic reaction. The enzyme concentration is actually small, and we want to get as much substrate. And our epsilon was exactly this ratio. Epsilon is E0 over S0. So then this is a small number, small compared to 1. Okay. So what we then do formally is we do an expansion of our solution, x and y, in terms of the small parameter epsilon. Okay, so expansion in epsilon. As I say, many of you, I assume, have seen such a method before. If not, well, here you go. It first looks a bit complicated, but it will simplify down very quickly. So we write x of tau to be a sum, n is 0 to infinity, epsilon to the n, xn of tau. Right, so then this is x0 plus epsilon x1 plus epsilon square x2, etc. And if epsilon is small, then epsilon to the n will be super small. So the higher order terms will be then become very small as well. And then y of tau, we do the same thing. N is 0 to infinity, epsilon to the n of tau. Good. And now we sub this in, okay? So where's my equation number 1? So wherever there's x, I put in the sum, and where's y, I put in the other sum, and it's going to get a bit cumbersome, right? So we have to replace everything here. So yeah, 1. Then get time. Yeah, I want to deal with the time derivative right away. So here, this is differentiated by time. The only time-dependent term is the xn, so we get a time derivative on the xn's. So then this term becomes n is 0 to infinity, epsilon n xn dot of tau, and let's use dot for the time derivative. Okay, on the right-hand side, we have some of
Then we have minus plus
r times this other thing plus y. Y is a sum epsilon n yn, and then in bracket we have alpha n. Okay, it's a bit cumbersome, is it? You can do this. Okay. Other one, I just copy from my notes, but you know what's happening. So yn dot. Worse.
Then once you understand
A method, actually you can get away without writing this down every time. You will get better, and then you will be able to see what's happening. So what do we see what's happening? So we got a whole bunch of sums and epsilons and xn's and yns. How can we make any sense out of this? Actually, that's a good question to you guys. Has anybody seen this? What do we do next?
What happened to the epsilon at the beginning
Oh,
of the y equation?
very good. Good point. Thank you very much. Yeah, so this is here, plus 1. Yeah, very good point. I shouldn't forget this. That's exactly why we do this. Okay. So the idea is now we compare orders of epsilon. So the epsilons, we have terms with epsilon 0, epsilon 1, epsilon to the 2, and so on, and we sort them by the power of epsilon. Okay? So this is called compare orders of epsilon. And the idea is that the equations should be true for any order independently. So for the order 0, for the order 1, etc., etc. So the lowest order then would be all those terms which have epsilon to the 0 in front. So let's go through all those terms here in our expansion and find those which have an epsilon to the 0. Okay, so then here on the left, it would just be x0 dot. Okay. If we go through the sum, anything else is higher with an epsilon to the 1 or 2 or 3. Then on the other side, same story. The only 0 term is the epsilon, the x0. And then here in this product term, so if n is 0, we get a y0. And then the alpha is just a constant. And we get the x0 from there, x0. Okay? And these are the only terms in the first equation which have an epsilon to the 0. Would you agree? If you find any other, let me know. And if I drop an epsilon, let me know too. Now, in the second equation, thank you for reminding me that we have an epsilon to the n plus 1. So then even if n is 0, the epsilon term is an epsilon to the 1. So which means we have no epsilon 0 term on the left-hand side. And then the other terms are the x0 term from there, minus y0 from there, kappa plus x0 from there. Yeah, okay. And so then, do I give this a number? I call this number 2. And x0 is not the initial condition. It is really the first term in our series expansion. So x0 is a function, y0 is a function, just to be clear. Now, let's compare 2 to 1. I don't know if I can maybe make this smaller just to compare in your notes. If you look at 2 and you look at 1, they have the same structure, except the epsilon d by d tau term is gone. And there we have a 0. So this is a shortcut, okay? If you do this ever again, you just say, okay, I'll remove this term where the epsilon is, and then I get the leading order approximation. So this is also called the leading order. The leading order equation approximation, let's call it approximation. So meaning if we solve 2, then we have the first term in our expansions here and here, which is expected to be the largest term because it has an epsilon to the 0 in front. So how do I want to formulate this? Yeah. Ta-da-dum, ta-da-dum. Okay. Now, so we could continue. Let's continue with this thing. So insert page. That's really funny. If you didn't use it for like 2 weeks, you have to relearn how to insert a page. Okay. So let's try just for practice the epsilon 1 terms. Let's see if we can get those together. Now, that page is not big enough. Let's do this then for the y equation because I can see the y equation right here. And then I write the x equation on top in a second. So for the y equation then, now we look for epsilon 1. So on the left, if we choose n is 0, then we get epsilon to the 1 times y0 dot. Okay, so here we get a y0 dot on the left. And then on the right, again, we look for n is 1. So then this is x1 minus. And then here in this product, if we choose the epsilon to the 0 term, y0, then the kappa has no epsilon. Okay, this was carried over in the other term, but the epsilon and xn, we can use the x1 term there, okay, which has order epsilon to the 1. Or we use in the first one the y1 term, and then we have to use the epsilon 0 term, which is this. So you could write out, there's a product of two sums, right? You could write out all the terms and then collect it hand by hand. I did this kind of in my mind, where I have the 0 order term times the first order term here, and then the first order term times the 0 order term there, and then together this is always the first order term. Okay, and then for the other case, it's not visible now on the slides, but just write it down. Minus x1 plus alpha y1. Same story, so here I wrote it in terms, okay, plus x0 y1 plus x1 y0. So same thing, if you have a product, you take the first order term times the 0 order term and vice versa. So you get all of this. Okay, so what happens here? Now, now we assume we solved already 2, and if we solve 2, we sub it in here, wherever x0 is and y0 is, and then we get a system for x1 and y1. And then we solve that for x1 and y1, etc. So let's call this 3. Yeah, I don't really need it for anything else, so I call it nothing. No name. Okay. So could continue to x2, x3, etc. But nobody does this. So typically people are happy with the zero order approximation, leading order approximation, which I am as well. Good. So let's solve 2. Let's solve this one. What do we actually get?
Sure.
Yes.
I don't get how the epsilon to the 1 like equations. I don't understand where they came from.
Where they came from? Yeah. Okay. Very good. It's good that you ask these questions. So you mean in particular these terms here?
Yeah.
Yeah. So let me take this one out here and do it separately further down. So we can write the first term is a sum of the y's. So we have y0 plus epsilon y1. Yeah, that's what I want. Epsilon square y2 plus and so on. And then here we had kappa plus the x's, I guess. Yeah. So then this would be x0 plus epsilon x1 plus epsilon square x2. And it depends how many of these you want to do. And now we multiply this out. Okay, so we get kappa y0 plus y0 x0 plus epsilon y0 x1 plus epsilon square y0 x2. So I just used y0 so far. I use y0 and multiply it with everything on the right. And now I use the next term, epsilon y1. So plus epsilon y1 kappa plus epsilon y1 x naught plus, and then we get an epsilon square y1 x1 plus epsilon cubed y1 x2 and so on. So now I used the epsilon y1 term. And I'm not bothered about epsilon square because this is epsilon square. Okay, and now for all those terms which have only one epsilon, which is this one, and this one, and this one. Okay, and these are the terms, I hope, which I had here. So this guy, I probably have a minus sign wrong. Do I have a minus sign wrong? Oh, there's a minus sign in front. Okay. Anyways, so they're all minus, yeah. But then these are the terms.
And is it like when you write out that expansion, is it y naught and not epsilon to 0? Why not? Because it's
It is both. Because
Oh.
epsilon to 0 is 1.
Yeah.
Right? So it is there, but you can't see it. Yeah, so. Okay. Yeah, and thank you for the question. Wonderful. So back to solving 2. Where's 2? 2, 2, 2. Now, 2 is a differential equation, but also a non-differential equation, just an algebraic equation in the bottom. So let's solve this first. This looks easy. So solve second equation of 2. So what was it again? Now it would be good to have a blackboard. Like if you have 4 blackboards, then you can see all the equations together. Okay, so we solve the second equation for y0, right? We can get y0 would be x0 divided by kappa plus x0. Okay. Y0 is x naught over kappa plus x naught. Again, remember y0, x0 are still functions of time, okay? They're not just numbers, they're functions, but we have a fixed relation between those two functions. So this means x0 and y0. Now let's write this as function of tau, okay? Lie on a manifold. So in phase space. Okay, a manifold is always, if you have an algebraic relation between functions, like here, y and x, y0, x0 satisfy a relation. then they defined a manifold in phase space. Let me plot this. So phase space is x and y, or in this case, x0, y0. And they're related like this. So how does this function look like? How does this manifold look like? Who can do this? Look at functions and know how they look like. Sumaira? Anybody in the audience? Just use Desmos and put it in. It's an increasing function. It's a linear at 0. So if x0 is 0, y0 is 0, right? And then it has an asymptote. If x0 goes to infinity, this goes to 1. So it looks like this. So here we have y0 equals x0 over kappa plus x0. And this is the manifold I call M. So let me introduce M. Yeah. So that's now the set of all points x and y, so that y equals x0 kappa plus x0. So nothing really happened. I just wrote it down in a maybe more abstract way. But this is the manifold, and this is called the slow manifold. So back to 2. So what does it mean for our system number 2? In our system number 2, the second equation now defines a slow manifold. This means the first equation, the differential equation, lives on M. So the first equation gives us the dynamics on M. Another thing we should notice is we have replaced y0 by this formula, so we can do that in the first equation now, and we get an equation for x0 alone. So I do these two things down here, or on the next slide. Page. Rotate. So then, so the first equation, yeah, right. The first equation of number 2 lives on M. So it describes the dynamics on M because this is what we have chosen. And then we can replace y0 by this ratio. So this is x0 over kappa plus x0. The kappa didn't come out nice. Kappa plus x0 times alpha plus x naught. Okay, so I replaced the y0. Now everything is an x0. It's an ODE in x0. What could be simpler than that? Everybody is reminded back to math, I don't know, 334 or...
Okay, let's try to get we find a common denominator. Not terms will disappear, so the x0 square term disappears. Just keep linear terms 0. Kappa is minus kappa and plus alpha.
All right, next. I call Q to be alpha minus kappa. Nice. So we solve ODE. Who remembers ODE theory, how to do that? You are smiling.
I have to remind myself.
Yeah, exactly, right? I have to remind yourself, exactly. So in the audience here, around the world, how do you solve this? You go to your trusted professor and ask them, or you find a book, or find a book. I don't know, Desmos can, Maple or MATLAB can do that too. So here we use separation of variables. Yeah. Long time ago. So of variables. So let's walk you through this because this is we write everything which has x0 on the left and everything which doesn't on the right. So we can write it at x0 dot kappa plus x0 divided by x0 equals q. And we leave the q hanging there, the right hand.
And then we multiply this out.
And now we can integrate this. We integrate
My time
first one is with the definite integral here. I integrate from 0 to. The next term is x at tau q gets a q2 minus q times 0.
Yeah.
Now, this is what I have in my notes as well.
And then I
Solve this for the tau dependent terms. I write this now as x0 tau plus kappa ln x0 tau equals at 0 plus at 0. Okay, I would love to solve this for x0 alone, but x0 plus log x0 I cannot solve. That's a transcendental equation, and I cannot explicitly solve this for x0, although I would love to, but you cannot have everything in life. Okay, so this is it, and here, because I'm lazy, I call this now x bar. This term has too many zeros, 0 and 0, so it's actually, it is the initial condition. Yeah, this is now the initial condition x bar. So then this would also be x bar kappa log x bar plus q at tau, q times tau. If you set tau equal to 0, then the q term disappears, okay, and then you get a valid equality for the initial condition. Good. Okay, this again, all is on M. So, so we also get something about the initial condition of y. So then y 0 at 0, which we call y bar, would be whatever is on M. And M is, again, where's M? X over kappa plus X. So that's what it is. So X bar over kappa plus X bar. That's an important relation which will show up later again at some point. Okay. Okay. Now, one thing happens here already. Typically, remember, we have two differential equations. So typically, we would choose an initial condition for x and an initial condition for y. But here, we find that these initial conditions are related. They need to sit on M. And this is why this is called singular perturbation, because we lose kind of a degree of freedom. We can only choose one. We can either choose x bar or we can choose y bar, but we cannot freely choose both. So the choice of y bar, x bar is restricted. meaning we cannot freely choose both. And that's why it's called a singular perturbation limit. That's why it's called. Singular. Okay. Back to face portrait. What did we do? What actually happened? So we have the X and the Y and the manifold M. So what I'm saying here then is that the initial condition is already on M, right? This is how we characterized M. So here is your initial condition. Let's call this IC. And then the solution with the logarithm, which I wrote down here, is the solution on M. So then this would be like the solution. And actually, I didn't care if it goes up or down. I think it goes, oh, it depends on the Q. Oh, yeah, right. Right. If Q is positive, we go up M. If Q is negative, we go down M. So that depends on the sign of Q. All right. So are you happy now? You shouldn't be. You shouldn't be happy because what happens if I choose an initial condition not on M? Okay, so let's say this is my initial condition. Well, then I'm not on M, so can I do this? What's happening there? Well, this leads then to the inner solution. This is the second part. Maybe I keep the different color. And now the inner solution. Let me remind you of initially my picture here. Okay, so now we have the outer solution. We are sitting on this low manifold, etc. What I'm now looking at is the inner solution. Essentially, how do we get there? And that corresponds to initial conditions which are not on M. Okay. So we rescale time. Rescale time to investigate a short time scale, meaning close to the initial condition. Short time scale. And I call this new time scale theta to be tau divided by epsilon. And remember, epsilon was small. So there's always confusion why theta is called small. No, what is it called? Short time scale. And tau is called the large time scale. Because if you think about it, if let's say epsilon is very small, and if tau is 1, then the value for theta is really large. So let's say epsilon is a 1,000th, and if tau is equal to 1, then theta is 1,000. So it's a very large number. So you could say theta is a large scale and tau is a small scale. But so here's a graph how you should see this. I'm plotting time on two scales. Time here in the tau scale and here in the theta scale. And let's say tau is days. Okay, let's say tau is days. So then I count the days 1, 2, 3, 4. But let's say epsilon is 10 to the minus 2. If I count the same distance in theta terms, I need to count much higher. So let's say theta is seconds. So then I mark all the seconds, second, 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 and then I'm here. So how many seconds is one day? Oh gosh, 3,600? Or is this minutes? It's minutes, right? Let's call this minutes. So then this is 3,600. And so then the minute scale, of course, is much quicker than the daily scale. And that's what I have in mind. So theta counts the minutes and tau counts the days. Okay. So then let's do our calculus thing. So then d by d theta, using Leibniz notation for the derivative, is d by d tau by d theta. You can also write this as a chain rule if you like. There are different ways to write this down. And then d tau by d theta So I need to multiply this by epsilon, then d tau by d theta is epsilon. So then this is epsilon d by d tau. Okay. So now we use this in equation 1. So 1 was our original model and very on top of our equations. Okay. So then we get the page. Then we get this. We get okay. So our previous time derivative d by d tau is now 1 over epsilon d by d theta, and then we can multiply with the epsilon. So what I get is this: d by d theta x is epsilon minus x plus y alpha plus x, and d by d theta y, and here the epsilon disappears from the second equation, kappa plus x. So then this will be equation number 3. Okay, so go back in your notes and do this replacement with the derivatives, and then you will see that this works. Okay, and then x0 is x bar, y0, y bar. Okay, so we smuggled the epsilon to a different term in our equations. Yoo-hoo. And then if we set epsilon 0 here, we get dx by d theta equals 0, which is a great thing, which means xn is constant, right? So this simplifies a little, quite a bit in the other direction. Since, again, we do this the first time, I do this a bit more formal, and I also use an expansion for this step in epsilon, and again, we collect orders of epsilon. So I write x as a sum of epsilon j. The only difference is I use capital letters now to distinguish between this case and the other case. So y j, j is 0 to infinity, j is 0 to infinity. Right? I just use capital letters so we are not confused with the previous expansion which we did. Okay, collect epsilon 0 terms. Can we do this now without writing down all the sums into the thing? Let's try. So number 3, on the left-hand side, the 0 order term will just be big X 0 dot. And then on the right-hand side, everything is multiplied with an order of epsilon. So there's nothing which has an epsilon to the 0. Okay, so we get a 0, a big fat 0. And then for the y equation, we get the 0 order term here. And everything else, we have to take the 0 order term as well. So x0 minus y0 kappa plus x0. Yeah, and as I say, all in capital letters. So do that. So this is then the inner solution. Good. Okay, back to our ODE theory, mass 334. At least that's what this is in Alberta. I'm sure you have different numbers. Who can solve this equation?
Everybody can. First equation means x. X will be 0. And then, of course, it's equal to b. And then the second equation. Okay, so how do you solve the
Second equation. Now x0 is a constant.
So then this becomes a linear
Model, a linear inhomogeneous. Who has a method up their sleeves? So to anybody online?
Try some Separation of variables again, perhaps with some organizing of
in this
one
Yes.
side.
Well, if you separate, then you first have to homogeneous part and the particular solution. Right? You stop this part
Yes.
with separation and then add a particular.
So this works as well. I would use creation parts. And I skip this, I just write on the solution. So in this case, I refer you to you get y0 of theta. X bar. 1 minus theta minus I can imagine if I write this out. And we have 0. We have x0 set theta at 0. And then e to the 0 is 1, so the 1 minus 1 term disappears. And the second term gives us the right part. Right, so where are we now? Now we solve the inner here. Time is here. Now theta was our initial time and tau was our time. Now we have solutions here. Start with x bar, and we have solutions here. We are sitting in manifold. So then the last question would be
Matching. How do we get them together? The middle. And there you do
Sorry to interrupt. Your microphone keeps going off, Thomas.
mhm. Okay, I reattached it differently. If this doesn't help, let me know. Does it help already?
It helps now, yes.
It helps now. Okay, good. Okay, let me know if it's unstable again. So matching in another solution. Yeah.
and look at the inner solution as epsilon goes to 0.
The idea of this approximation is it should be good when epsilon is very small, right? So or super small. It should be the more small.
Let's look at the inner solution. So then if epsilon is positive, the large number in the inner solution is kind of here. And if epsilon gets smaller, then this inner region becomes smaller. So that's called epsilon very close to epsilon is equal to 0. Then this becomes
Here. So as seen from the inner solution,
this value corresponds to the limit as theta goes to
And
can't-
you're cutting out again.
yeah. Let me use the other one. I don't know if Shane is listening in. This is on. So here's a stand-up microphone. Do you hear me here better? Want to
Yes.
check? Yes. Yes. Good. Okay. It's probably just the battery down for this one. So where am I? Limit to theta to infinity. So to get to this boundary here, as epsilon becomes super small, this corresponds sending theta to infinity there. Okay, let's look at this limit. Limit theta to infinity of x0 of theta. Well, capital X0, right? This is the inner solution, was a constant anyway, so there's no real limit. This is x bar. And limit theta goes to infinity of y. 0. Oh my goodness, my writing goes out the window. Let's do this again. Limit theta goes to infinity of y0 of theta. Okay, there we have to go back to the formula. We had this interesting formula just a moment ago. So let's take the limit as theta goes to infinity. Okay, so e to the minus something theta goes to 0. This term appears twice. And then what we keep is a term 1 from the bracket times the factor in front. Okay, so then this is x bar over kappa plus x bar. All right. So let's give this a star. And now we look at the matching condition for the outer solution. What does the outer solution do for the same limit? Okay. So I plot again the three graphs. So here when epsilon is kind of large, then the outer solution sits here. If epsilon gets closer to 0, it gets here. And if epsilon is equal to 0, it will be the limit as tau goes to 0 of x of tau. Oh no, this is little x, little x. Little x0 of tau. Yeah, I hope this is clear enough. So that, which means for the outer solution, we look at the initial condition. Let's do that. Limit tau goes to 0 of the little x0 of tau. And we need to go back a few pages to find that. So little y0 of tau. So let's go back and see where the initial conditions were from the outer solution. Here. This was this one. This was this case where we said the initial conditions are related on the slope manifold M. So then, okay, then we have, what do we have? So then this one is the x bar, and this one is the x bar over kappa plus x bar. Okay. And wouldn't it be nice if this matches the previous one? Does it? Yes, it does. Okay, I have to make it a bit smaller. It does. It is exactly star. Yoo-hoo, this gives a big smiley face. So, so this is how the matching works. And this tells you then at this stage, you did a good job and you did your calculations right. And this works in this case. And as I said, there are cases where it doesn't, okay? And there's no need to be desperate or so. It just can happen that it works, so it can happen it doesn't work. So in this case, it works fine, which means we closed the gap here with this question mark. We know that this limit on this side and this limit on that side, they coincide, and so we can match them together. Okay. How does it look in phase space now? There's still one thought we have to do. Okay, so maybe I first want to write this. So in general, we have limit theta to infinity of the inner solution equals limit tau to 0 of the outer solution. Yeah, I think this is something you should actually remember for your entire life. It's a good thing to know. Okay. Then I switch to black, putting this together in phase space. So then this and this again. Here is the manifold M. Here is X. Here is Y. And then we said we use the inner solution if we are not starting on M. So let's use this as an initial condition right here. So then the inner solution says X doesn't change. Okay, so X doesn't change. And in this case, we go up straight to M, and then we settle on M, and then we follow M slow. And so I do a double arrow to indicate fast, and then I do one arrow to indicate slow. And then this is the dynamics. So this is fast, and this is slow. And the slow happens on M, and the fast happens off M. Nice. So what is now my time here? Okay, so then in the last, what do I have? Yes, I still have 20 minutes, 25 minutes. I put this in context of a bit more theory. I tell you about the Finical theorems. Yes, and then next lecture we use this for the tumor growth paradox. Oh yeah, this is going to be fun. All right, let's do theory now in purple. So a bit more theory. And these are the famous Finical theorems. So I'm not going to go through the proofs of the Finical theorems, but I want to generalize this just a little bit. So we did this at this Michaelis-Menten example right here. But of course, the method can be applied much wider than just this. And let me just talk about this a little bit so you would be ready to use it. So there is a wonderful text. And Sumaira, if you can find this and put it on the website, that would be lovely. So by Hig, Journal of Mathematical Biology, which is called Geometric Singular Perturbation Theory in Biology from 2010, volume 60, pages 347 to 386, where this method is summarized on a more general level. So we start with an ODE system. And now I write it down in U's and V's. So U dot is F of U and V and maybe epsilon. And V dot equals epsilon G of U and V and epsilon. So this is 1. And we can do the rescale system. Rescale system where we scale time again. Now I use tau to be epsilon T. Right, earlier I worked with theta and tau. Now I work with tau and T. So anyway, so we get an epsilon here. U prime is F of U V epsilon. And V prime is G of U and V and epsilon. Okay. And let's call this 2. Now, this looks a little bit different than what I did just before, and we need to wrap our head around this a little bit. So which of them is a fast and which of them is a slow system? Maybe I go back. Let's go back. Again, I wish I have like 12 blackboards I can write on at the same time. Leading order approximation. Fast. Where's my? Here's my fast. This was a slow. Right. and here as well. Okay. So we started having the epsilon in front of the time derivative d by d tau. This is how our model appeared. Okay. And this was then our slow system. So where is this here in the general theory then? In the general theory, it is the second one, right? So here we have the epsilon multiplying a time derivative. So this will be our slow system. Which then means, of course, the other one will be the fast system. Okay. Insert page. So then in either case, we can do this expansion thing again, but it led to the effect that we just get the leading order terms. So then we have leading order fast. Just setting epsilon to 0 in the fast system. So we get u dot equals f of u and v and 0, and v dot equals 0. Okay, this was a fast system, and for the slow system, leading order slow, we get the opposite. So now we set epsilon 0 in the second part. So then we have f of u, v, and 0, and v prime is g of u, v, and 0. Right, and then for, let's keep the numbering, 3 and 4. Now in 4, the first equation in 4 is just f is equal to 0. So this defines again our slow manifold. Slow manifold. Let's write it down properly. So then the slow manifold is all u's and v's, so that f of u v 0 is equal to 0. So are they done with their coffee break outside?
Yeah.
Yeah, very good. It got a little bit noisy out there. Okay. And then as we had, right, the slow manifold is something in phase space. And if u and v are vectors, right, then the slow manifold will be a codimensional one submanifold thingy. So it could be rather complicated as well. So I assume f and g are C1 functions. So continuously differentiable. And then I introduce a definition which I have not used in our example, which is called normally hyperbolic. So the slow manifold is called normally hyperbolic. And this is actually a very natural assumption, a definition. And I explain to you what it is. If the eigenvalues of the Jacobian of df by du on the manifold, so at uv0 on M, are uniformly hyperbolic. Hyperbolic. Okay, so this is a terrible definition, right? I mean, what does this mean? What the F does this mean? So I tell you what this means. I need a bit more space, I guess. Next page. So here it is again. So you remember a hyperbolic fixed point is a fixed point where the eigenvalues have no real part equal to 0, right? And this was what we earlier used in the Hartmann-Grobman theorem, for example. So if a fixed point is hyperbolic, you can talk about a stable or unstable direction. It's a node or a stable spiral, etc. Only if it's not hyperbolic, we can have a center or eigenvalue equal to 0. And the same is now applied for a manifold, but a manifold is a manifold. It's not a point. So we can only talk about hyperbolicity in perpendicular directions to the manifold itself. So for example, I plot a manifold. Now a manifold can be something manifoldy, M. And normally hyperbolic means in perpendicular direction, let's say it's attractive. Okay, from on top or from the bottom, it's attractive. It could be repulsive as well, right? But that's what I mean by normally hyperbolic. So this is normally hyperbolic. And a way to express this is to linearize on the manifold and look at perpendicular directions to see if the eigenvalues are attractive or repulsive. So a counterexample of not normally hyperbolic, how would this look like? Not normally hyperbolic. Let's maybe plot the manifold just a little bit different. So let's call this maybe M. And it could happen that the vector field just touches. So if the vector field goes like this, touch, and goes up again, here it goes down, here it touches, here it goes up. Okay, then at this point, which I indicated here, it is neither attractive nor repulsive. The eigenvalue would be 0 of the Jacobian. And so this is a not normally hyperbolic case. So I think graphically it is quite intuitive. To compute this, well, you have to find the eigenvalues of this Jacobian here, which is also not too hard to do. Yeah, so once we have this in place, we can finally write down the Fennikel theorems. There are 2 of them. So Fennikel 1. So we suppose M0 is normally hyperbolic. M is normally hyperbolic, as we just defined, and compact. All right. Then for small epsilon, yeah, then for epsilon small, there exists another manifold which is nearby, a manifold. Let's call this M epsilon. That is, and then it has 3 properties. So first it is O epsilon close to M. So this means if epsilon goes to 0, this manifold M epsilon goes to M. Yeah. It is a diffeomorphic to M as well. So which means there's a map, a differentiable map, whose inverse is also differentiable, which would map M epsilon to M. And then locally invariant for the nonlinear ODE, for the nonlinear system, for the full system. Yeah. Okay, so how to plot this? It's always good to have an image in mind. What this means is, so let's say this is M, okay? And on M, we solve the slow system, right? So then we have a slow system here on M. And now it says the real system, the original system, has a manifold which is super close by. So maybe I plot it just underneath a little bit. This would be M epsilon. And then the corresponding orbit would also be close, but a little bit maybe underneath. So then M epsilon is actually the real thing, and the purple M is our approximation. And it says the approximation is actually really good. It is very, very close. Okay, and then there's a second part, which I show you as well. Purple. Okay. Fenical 2. And this talks about stable and unstable manifolds. So in addition to the previous one, there exist stable and unstable manifolds. Let's call them VW stable of M epsilon and W unstable of M epsilon. That are epsilon close. O epsilon close to the stable and unstable manifolds of M. And respectively. Okay, so this also needs a picture. Let's consider the same picture here. This is my manifold M again. We said normally hyperbolic, okay? And the normally hyperbolic was the fast dynamics. So the fast dynamics drives it down. This is what we did with the inner solution. And this would be the stable manifold of M. And so the Fenical 2 says that also here, close by, there's the stable manifold for the real system, M epsilon. You know, and in my graph, M epsilon was a little bit underneath. Oh, this is not so easy to plot. So M epsilon. Okay. So then Fenical 1 says these manifolds M and M epsilon are close, and Fenical 2 says that also the approach is close. Yeah, and this is exactly what we did. Nice. Good. So this is essentially what I wanted to do today. Time is awesome. We can finish here and then we continue. Oh yeah, next week is a conference, right? Next week is a conference again. So you can use the evaluation form online if you want to follow some talks and evaluate them and give some feedback. And then our lecture continues on October 8th. And then Natalia Komarova is again on October 10th. Yeah. Thank you very much. Any questions?
There was a question online from earlier.
So why does Q, or why did Q dictate the direction? This was long ago, but I can still go there. I can still go there. So this was our solution here in the box, okay? And the Q is this term. So if Q is positive and tau increases, then the entire thing grows. If Q is negative and tau increases, then the entire thing becomes more negative or becomes smaller. So that's why. Other questions? Okay, if not, thanks very much. Questions from you guys?
I don't know if I've seen this before, or if I'm just,
Fair enough. Okay, yeah,
Yeah.
good. Yeah.
I gotta read about it. I don't think I've ever, I don't know how I missed.
So
I just thought,
yeah, this perturbation analysis typically taught in the beginning graduate classes, I would say. So not an undergrad. Yeah.
I did take, I have a master's, so I don't know, maybe I learned it and it just like thought about it.
That is possible too, sure.
Yeah, because I think the ODE course that I took in graduate school was like 3 years ago now. So, and
Oh,
I
you
probably
wouldn't
haven't
do that.
looked at
You
it.
wouldn't do that in the OD course. It's typically not in the OD course. It's
No.
like more in like a modeling course or techniques in applied math course.
Oh, I don't think, I didn't take any.
Some of
of it.
those, yeah.
Yeah,
Yeah.
so,
So then fair enough.
Yeah.
Okay.